Welcome to our short explain video on the impacts of choosing different basis functions to model data. First, we want to give a very short recap on what basis functions are and why they are this important. Then we will introduce or better reintroduce you to the different categories and types of basis functions we can use for linear regression. At a last step, to bring some life into this topic, we will show on real-world examples what the different models are being used for in practice. As we already saw in the last couple of videos, our goal in linear regression, or regression in general, is creating a model that fits our data well, to predict further hypothetical data points or understand correlations. To do this, we choose a specific model with an underlying basis function to approximate the data with the lowest possible error while avoiding overfitting. We already know how to compare different models by computing the corresponding AIC score. But speaking more generally, we always tend to have the same problem at the beginning of selecting a model for data we want to fit. Which type of function should we use for our regression? Because oftentimes the models with linear and even the polynomial basis functions describe data either very poorly or are getting unnecessarily complex. In the next couple of slides, we will introduce you to the different categories and types of possible basis functions to model our data using linear regression and visualize the corresponding change of fit. We selected different basis functions and mapped them to the same data to show you the importance of choosing an adequate underlying basis function for your model.
Before jumping into the different categories of basis functions, we shortly want to recap on the two most basic regression models we all already know. The simple linear model using an underlying linear basis function and the polynomial model using an underlying polynomial basis function. In the following, we will map the different regression models on this imaginary dataset right here, before moving to real-world data. This simple dataset helps explaining the core differences of choosing different basis functions. Here you see the simplest linear regression model called the simple linear regression. It is visually obvious that this model is not a good fit for our data at all, but there are still some applications for it, as you will see when we are talking about real-world examples. The second classical example for linear regression is the polynomial model. Here you see two polynomial models. On the left side, degree 2, and on the right side, you can see one of degree 3. So far, so good. Apart from these two commonly used examples, there are several more mainly contained in three major categories, namely global, relatively local, and strictly local basis functions. Each category comes with their own advantages and disadvantages depending on the properties of the data and our hypotheses. The categories of the basis functions depend on the corresponding range of the functions. For global, this means the function extends over the whole length of the x-axis. The strictly local functions only extend over a closed interval and can therefore only model data in this interval. The relatively local functions are theoretically also global, but the actual impact of the function remains inside a small interval as well, similar to the strictly local basis functions. In case of relatively local and strictly local, the basis functions mostly consist of multiple, individually defined parts.
On the left you see a normal Gaussian distribution, and on the right you see a Gaussian model with several underlying Gaussian distributions. Due to their relative locality, meaning the significant impact of the function is limited and almost zero outside a certain interval, for example the credible intervals, a combination of different Gaussian distributions can be used to approximate our data by adding different Gaussian forms to one function, each one with individual mean and standard deviation. A powerful alternative is to define basis function piecewise, meaning the function is independently defined for certain intervals. In the first picture you can see a linear regression using a bin-based linear model. The knots where the bins connect are shown as the gray dashed lines. This already is a big step up for our model if you remember the simple linear model. In the second picture we added some more knots, making the model more precise, yet a little more complex. A big advantage of these bin-based functions is their locality, meaning a change or addition of a data point does not affect the whole curve. A significant problem we still have with this kind of piecewise definition are the knots connecting the bins. Our model here is not smooth at all. To solve this, a different kind of bin-based function is more suitable, the binwise polynomial.
As you can see here, the binwise polynomial is not only connected to the adjacent part of the function, but it instantly looks like a smooth function. One could say the parts blend into each other. They are continuous. The different levels of continuity measure depend on the amount of derivatives of adjacent functions matching at the nodes. This so-called continuity measure is defined as Cn, where n stands for the amount of derivatives matching. If the functions don't match at all, C is defined as C minus 1. C0 would be, for example, the case of a linear piecewise function, which you saw on the last slide. The functions depicted in the graph are cubic splines with continuity measure of at least 2, where each bin consists of 4 smaller parts with polynomials of degree 3. What does that mean? So let's quickly talk about the different segments inside one bin to get an idea of how these piecewise functions are defined. In our case, because we are talking about a special type of binwise polynomial, the cubic spline, each of our bins is defined by 4 different parts with polynomials of degree 3, combined in one function. You can see the 4 segments separately defined over the interval here.
If this still seems a little confusing or overwhelming, you can check out the interactive model yourself and play around with some imaginary data in different regression models and see how they behave when changing data points. For example, you could check out the linear, the polynomial, or the cubic spline model. Now you know that depending on the properties of your data, you should use different basis functions to improve the fit and obtain a less complex model. In this part of the presentation, we want to introduce you to some real-world examples and their corresponding regression models. Let's return to our starting example for a second here. In case of our data, the model wasn't a good fit at all. However, there are some real-world applications for it. Here you see linear regression used for predicting the average temperature increase in Canadian winters. On the x-axis, you see the years from 1950 to 2010, and on the y-axis, you see the mean temperature. The simplicity of the linear basis function really comes in handy in this case, because of our goal to capture a more general trend and not short-term changes. Depending on our data, but also on the research question, a linear basis function can still be a valid choice. This slide shows the relationship between age and triceps skin fold thickness measured in logarithmic scale for 892 female participants in West Africa. Skin fold thickness describes body fat and therefore indicates the body composition of the participants. The different colors indicate the different models describing the data. Here you see various different basis functions in action. The black line is a polynomial fit versus 3 different spline fits. The red line is a B-spline fit, the green line is a natural spline fit, and the blue line is a smoothing spline, all defined with 4 degrees of freedom. Here you can see that each model describes the data slightly different, and the model comparison will yield the best suited model.
Understanding temporal changes in disease occurrence in human populations is one of the priorities of epidemiology, public health, and life science-related disciplines. A topic we sadly are more than familiar with at the moment. Understanding temporal changes in disease occurrence implies the ability to describe and examine temporal patterns, which include increasing or declining trends, here called seasonal patterns. It also needs to describe unusual spikes associated with outbreaks or disappearance of periodic episodes, showing that treatments are working. Here, seasonality is defined as systematic, repetitive, periodic fluctuations in disease incidence over the course of 1 year. These measures allow to compare seasonal patterns across diseases, locations, and even populations. They are modeled using sine and cosine functions. Sine and cosine functions are used because they are smooth and symmetric and thus are appropriate for diseases that exhibited steady seasonal rise and decline, which would be much harder or even impossible with other models and their underlying basis functions such as the polynomial, for example. The models A to D you can see on this slide are all variants of parametric Poisson models, which are called harmonic regression models. These harmonic models are based on sine and cosine basis functions. So, in conclusion, what should we take from this? Basis functions in general determine the type of function used for our models, so the underlying function. Which type of model to choose depends on the data as well as the hypotheses. How good a model is to fit our data does not only include how well it fits the actual points, but also how complex it is. This can, for example,